So let's start with a talk by Niels Obers.
Thanks a lot. Yeah, let me also thank the organizers a lot for putting up this fantastic workshop and giving me the opportunity to tell something. So I'm going to talk about non-relativistic corners in string theory in AdS CFT, something I've been working on actually for quite some years, and a paper coming up together with various collaborators. Just to sort of zoom out and illustrate sort of the overall philosophy that this talk takes place in, I remind you here, and most people have seen this, I think, of the Bronstein cube of physical theories. I just want to say this is just a very rough picture of the philosophy. It's not that I precisely know what these corners mean, but it's more like the framework in which we can think about physical theory. So I'm sure you have seen it. We can think of the three constants of nature: Newton's constant, 1 over the speed of light, and Planck's constant. And then we have different frameworks in physics to do things. And in particular, I think what unites us here in this conference is that we want to understand this corner, quantum gravity, and in particular also its realization as a string theory. Actually, very often when we approach quantum gravity, we approach it from the field theory corner and say, well, we understand the rules of field theory, let's turn on gravity. Or from this corner, GR, we understand classical gravity, let's try to quantize it. But if you sort of think about this corner, this cube, it seems there's another corner here, NRQG, and I'm not claiming to exactly have a precise definition of it. Let's call it non-relativistic quantum gravity for now. But that if you could understand this, maybe there's another third route to approach questions in quantum gravity. And also, just like we're celebrating here, the celebrated AdS-CFT duality, which you can see as a duality between these two corners. Likewise, this cube suggests some kind of maybe simpler duality between corners like this. And I should maybe also mention already that I put here NRG, non-relativistic gravity, which would be the classical limit of whatever NRQG is. I just want to emphasize that one of the things we have learned, not so much from looking at string theory, but more carefully examining the large speed of light of GR, that actually already this corner is something more general than Newtonian gravity. So the arena in which this talk is taking place is the question, how does string theory and holography fit within this overall picture? Actually, a lot of recent progress in understanding non-relativistic corners more generally of gravity, quantum field theory, and string theory. Much of the recent progress, in fact, builds on an improved understanding of the geometric picture behind it, which goes under the sort of general name non-Lorentzian geometries. And you should always be very careful with names that have a non, but it roughly means space-times with local symmetries other than the Lorentz symmetry that we all know and which underlies Riemannian geometry. And there's actually a whole slew of applications of non-NL, non-Lorentzian geometries. And I just already say I'm definitely not going to talk about all of them. The focus of this talk is the last two applications, but just to put it in a slightly larger perspective, they have been seen as boundary geometries in non-AdS holography, for example, Lipschitz spaces. They appear in covariant formulations of post-Newtonian approximations in GR. They have actually also played a quite useful role in covariant formulations of non-Lorentzian fluids and CMT systems, and actually one of the originators of that, Damson, is in the room here. Also, looking at the title, we might see some more about that in Damson's talk. In fact, also very recently, such non-Lorentzian geometries play a role in formulating fracton hydrodynamics. However, Lipschitz gravity, then there's also the whole developments around not the limit or the expansion of large speed of light, but small speed of light, c, going to 0, which goes under the name of Carroll. Also there has been quite some developments related to applications in cosmology, black hole horizons, and flat space holography. But anyway, after this whole wash list, this talk mainly concerns these two topics. And before I give sort of the punchline, or not the punchline, but the main message of the talk, of course I want to give a slightly more specific motivation of why you could be interested in non-relativistic, so I often use the abbreviation NR, string theory. That is string, we know a lot of string theory, but there's always more to learn and more to uncover. So you can ask, can we learn more about ordinary string theories from NR techniques? And might have some suggestions. A maybe more ambitious question is, what is the landscape of ultraviolet complete non-Lorentzian theories? In that connection, actually, I should mention, it was also on the previous slide, that double field theory actually naturally incorporates certain non-relativistic strings. Other obvious motivations are what's the role of D-branes and open strings in non-Lorentzian string theory. The one I already mentioned, can we build explicit examples of holographic dualities? And a bigger question, is NR2G a well-defined corner, and does it have a string theory description? Go forward. So, yeah, what I want to sort of explain in this talk, and I'll try to be not so technical, but yeah, we'll have to do some technicalities. But the main message is, first of all, I want to show for you, or argue, that non-relativistic strings actually naturally appear in the AdS CFT correspondence. That if you consider, in a way that I'm going to show in a second, near BPS limits in n equals 4 super Yang-Mills, then non-relativistic strings naturally appear. That's point one. And in particular, we have a concrete sigma model realizations of these non-relativistic strings arising from near BPS limits. But the second important point that I hope you come away with after this talk is that these resulting sigma models here, in something very specific, starting with n equals 4 super Yang-Mills, are actually part of a much larger landscape of non-relativistic string theories. Actually, non-relativistic string theory in flat space-time already dates back to, well, not 25 years, but 23 years, to 2000, and work by Gomis and Oguri, and also Danielson et al., where this was the time that all kinds of corners of decoupling limits in string theory were examined. And one interesting decoupling limit that these authors found was by looking at closed strings with a near critical B field, and I will review the action for you in a second, give rise to a non-relativistic string theory. What's more modern, and is more like developments from the last 5 years, is the question is, so in a sense, this NR string theory has been dormant from a certain point of view for 23 years, but is the question, is there a curved space-time generalization of these NR string theories of the 2000s? And I should, by the way, say that these here, they're still two-dimensional worldsheet CFTs, but they have strings that are probing non-Lorentzian target spacetimes. And so, yeah, where the link is from here to here is basically by looking at the larger class of non-relativistic string theories of this type, that by doing a further worldsheet limit, starting from these string theories here, one can find something that we call a Galilean string. We call it Galilean because now the target space is not only the target space that's non-Lorentzian, it's also the worldsheet that has Galilean symmetries. And it's that class of sigma models that connects to these near BPS limits of AdS CFT. And yeah, I'll not have time to give any details, but just to say, there's actually also a dual limit here that gives a so-called Carolian string. Maybe, yeah, I can spend 1 minute on it. I keep going the wrong way. So, what's the heuristic, or well, slightly more than heuristic motivation? There are many details that I'm not showing you here, that NR strings naturally arise from n equals 4 super Young Mills. And it goes back to a paper by Harmack and Orselli, where they find so-called spin matrix SMT limits of AdS CFT by zooming in on unitarity bounds of n equals 4 super Young Mills on R cross S3. The limit taken is essentially look at the energy difference between, well, with some kind of BPS state Q. Q can be, in general, some linear sum of Cartan charges, both on the AdS5 and the S5. And look at the scaling limit where you send lambda to 0, but you keep this ratio fixed. What they showed is that in this limit, n equals 4 super Young Mills simplifies and becomes a quantum mechanical theory with a well-defined Hamiltonian that actually reduces to nearest neighbor spin chains in the planar limit. Now, what we know very well how the low energy excitations of spin chains can be described in terms of magnons. Of course, I omit here some really important reference, notably from, of course, Minahan and Zarembo, that found for the SU2 case the Heisenberg spin chain. But so more generally, Bisert found a general magnon dispersion relation for the most general spin chain, which is this formula here. Now, you can clearly see that this SMT limit precisely gives a dispersion relation like so. So this is a relativistic one. This is clearly non-relativistic. Of course, there's a sign here because of the discreteness, but in the continuum limit, you precisely see here that the energy of the excitations are proportional to p squared. And in fact, as is known from work by Kruczynski, precisely in the semi-classical limit, such spin chains become sigma models. And let's say the simplest one, again, in the SU2 sector, would be this Landau-Lifshitz model. So I will show, I'll now take a step back and start to discuss non-relativistic string theories a la Gomis, Oguri, etc., etc. But I will show that such models here, and also for other BPS limits with more general Cartan charges turned on, are part of a larger class of Galilean string models that I will obtain along the way. Is there any questions at this point? Okay. Yeah, okay, that's for the, so let me just repeat the highlights that precisely using the AdS CFT dictionary, these near BPS limits can be formulated as a limit on the space-time, on the AdS for cross S5. We'll see that they give rise to non-relativistic Walsh-Heat strings. And it's maybe interesting to see that this actually suggests that this particular corner of n equals 4 super Young Mills, which might be more tractable because it's a quantum mechanical theory, has a bulk description, semi-classical bulk description, in terms of some non-relativistic gravity, some dynamical non-relativistic gravity. Okay, so I guess you're asking, how can it be that in a weakly coupled limit we get strings? So, but we get this, so the sigma model is obtained in the large J limit. So in a sense, it's the large J limit that makes the spin, the spin chain in a continuum that gives it the stringy behavior. But it's a very good question. But because you could wonder, how can it be that the weakly coupled Young Mills? But so it's actually kind of, well, not mysterious, but kind of unexpected. Okay, I'll get there. Yeah. So I'll speed up a little bit. this is many references. I just want to say, emphasize again that Komesu-Gori found non-relativistic strings on flat space-time. Work of the last 5 years has shown how to generalize it to the curved spacetimes, and that's what you want to see the details of. Just very quickly, what are we finding the curved space generalization of? Here's the result that these authors got. Look at the zero Regge slope limit of a relativistic string theory in a near critical B field. Gives an action like this, where this is the wall sheet metric. In conformal gauge, this is the action. These axes are transverse to the wall sheet, and these are light cone directions on the wall sheet. And you can show, it was already shown in this beautiful paper, that string theory has, first of all, a Galilean invariant dispersion relation, no massless physical states. By looking at, so all the physical states have at least some non-zero winding. And by looking at scattering of non-zero winding states, it was shown very beautiful that the low energy effective theory of the string theory is described by Newton-like gravity. And okay, I emphasize this. All asymptotic states carry some non-zero winding around a compact x1, which is one of the directions. So this is x0 plus or minus x1. And x1 is the compact longitudinal space-like direction. So the question is, how can we generalize this to a non-Lorentzian space-time? And this is where the concept of Newton-Cartan space-time comes in. In a nutshell, I'm not, what Riemannian geometry is to local Poincaré symmetry is what Newton-Cartan geometry is to local Galilean symmetry. I find it quite beautiful that, in fact, that's then 100 years ago, in 1923, Cartan realized that, okay, Einstein geometrized gravity, but that's not a specific property of Einsteinian gravity. You can also geometrize Newtonian gravity. It's more like then you have another equivalence principle that freely falling observers see the laws of Galilean physics. And that's what Newton-Cartan geometry does for you. So what, this is now not the stringy Newton-Cartan geometry yet, but a precursor. Let's call it particle Newton-Cartan geometry. Important part of the talk is to explain you what the stringy version is, but it's easier understood by first understanding the basics. So instead of a metric, there are three, the metric is replaced by three tensors, a time-like field line, tau mu, and they're still tensors. So you have diffeomorphism invariance, or covariance. A metric on spatial slices. So this h mu nu is a degenerate metric with a rank d-1 in d dimensions. And very importantly, and that's part of the geometry, there's also a vector field, mu, which you can see as the gauge field of mass generators. Another very beautiful way, now I didn't put the transparency in, and that's also what Damson pioneered. Precisely, if you take not a relativistic quantum field theory, but a quantum field theory with non-relativistic Galilean global symmetries, then this is the natural geometry to which you would, natural background geometry to which you would couple this. And precisely mu, and we'll see it in a second for a particle, mu would couple to the mass current, whereas tau mu would couple to the energy current. And energy and mass are not the same in Galilean theory. Here's then, so if you would want to write down, which I do here, the coupling of a non-relativistic particle to this geometry, and maybe I didn't stress it, but this geometry can have, I'm going the wrong way, it can have torsion, but in view of the time, I will not dwell on that too much. But if you want, there are two actually nice routes, and I emphasize them here because you can follow the same route for the string. There are two nice routes to get the covariant coupling of a non-relativistic particle to this geometry. One is you can take the action of a relativistic particle and null reduce, And the other is you can stay in the same dimension and look at an extremal charged particle and take the large speed of light limit. And that gives you this action. You see here the geometric fields. And if you close your eyes, you see here precisely, right, mv squared plus phi plus the coupling of a Newtonian potential to the mass. And this is the covariant form of it. So this is the kinetic term, and this is the potential term. And indeed, the response to varying mu is precisely the mass current. So nothing too mysterious here. But this should give you a feeling of what Newton-Catan geometry is and how you can write down actions. And you can also do, write down covariant actions, say, for a Schrödinger field coupling to this background geometry. It has various nice applications in the fractional quantum Hall effect. So the sort of the obvious guideline is to get the generalization of Gomis-Oguri for arbitrary curved space-time is to take the same route, but now for a string. And again, you can distinguish two paths. They actually has been checked in detail, give the same result. You can either do a null reduction of a relativistic string action, and that actually involves something like a light-like T-duality along a null isometry. Incidentally, for those people who lived pre-2000, this is intimately related to the DLCQ of string theory, and in some sense gives a more conventional description. So non-relativistic strings give a more conventional description of the DLCQ. So that's one way, but you can also not stay in the same dimension and do natural generalization, but then in curved space-time of what Gomis and Oguri did, and take a C to infinity limit in a near critical B field. And incidentally, the string is perfectly set up to do this because strings are actually really extremely charged under the B field. As we all know, that fundamental strings have the property that tension equals charge. This is a crucial property that ensures you that in this limit, infinities will cancel. So string theory is really set up to do this limit. And then, you find the strings. I will give the action in a second, but before giving formulae, the analog would be what's called torsional string Newton-Catan geometry. It's essentially a Riemannian geometry in the transverse space, transverse to the wall volume, fibered over a two-dimensional Lorentzian base, which is the longitudinal one. And I emphasize that you still have a Lorentzian metric on the world sheet in these theories. And as I said before, that means that they're still two-dimensional CFTs. It's just the target space that's different. So what are the actions you get? Let me first, before talking through the action, give you the geometry. In a sense, you could almost guess, well, if you stare a little bit at Newton-Catan geometry, what a stringy generalization should be. Remember, in Newton-Catan geometry, you had a time-like field line and a metric on spatial slices. We now don't have a particle, we have a two-dimensional world volume. So there will be another world volume index A, 0 and 1, associated to tau. Transfer space will still be h mu nu. And again, since particles carry a momentum current, likewise strings carry a tension density current. So you would expect a two-form field in the geometry. And that's precisely what you get. And the Namu-Goto form of the action looks like so. I didn't go through all the definitions, but alpha and beta are world sheet indices, and these are the usual pullbacks of these space-time fields. You can maybe get an impression. So there's a kinetic term and a potential term. And like I said, this mu nu couples to the generalization of a momentum current for a string, which is this tension current. There's also a corresponding Polyakov action. that now involves these Lagrange multipliers, which you can see is the, well, if you do this on flat background space-time, you get the Gomis-Ogurius action. What are the symmetries? Well, so this is where the non-Lorentzian nature. So far, I don't know if saying what the geometry is satisfied you. Of course, I have to also say, to define the geometry, I should also tell you how the local symmetries act on it. To not make it too technical, I didn't do that for the Newton-Catan case, but this is how it works for the string case. The essence is that there's no Lorentzian boost anymore, but there's Galilean boosts in the transverse directions, parameterized by a boost parameter lambda AB. So again, for a particle, it would be just, there wouldn't be a Walsh sheet in this A, so lambda B would just be a Galilean boost parameter, like the velocity, say. Now you have a matrix of Galilean boost, and yeah, under such transformations, you can see that the actions are invariant, and you can actually also make corresponding connections and curvatures that are invariant under these symmetries. So there's a whole generalization of Riemannian geometry that you can use to actually build, for example, two-derivative effective actions using these geometrical ingredients. So we have so-called transverse string Galilean boosts and still longitudinal Lorentz boost. And like I said, that's the string analog of an NR particle. Maybe some remarks, and obvious question is, and many people have looked at that, what can you compute beta functions for this non-relativistic string theory, and what does it look like? And using various approaches, they have been computed, and they will give you effective space-time actions built out of these geometric objects. So they describe the dynamics of some version of non-relativistic gravity, and some very ambitious people have actually also already generalized this to some kind of supergravity version. I'll skip the limits versus expansions view of time. Now, I hope it's very clear. So far, I've defined for you 2000s non-relativistic string theory on a curved space-time. Where does the connection come in with Walsh sheet models that are related to these near BPS limits of AdS CFT? For that, you have to actually do a further limit, but now on the Walsh sheet. So in some sense, it's a double non-relativistic limit. I've written here again the action that I wrote before, but now I've put a parameter C tilde between the two field binds on the Walsh sheet. There's a field bind on the Walsh sheet going in the time-like direction on the Walsh sheet and the space-like direction. And you can put a parameter in between that you morally can see as the speed of light on the Walsh sheet, as opposed to the speed of light we had before in the target space-time. So, for motivations that will become clear, but you can take a certain limit where you also send that to infinity. That gives this action, and that's what we define to be the action of the Nambu-Goto action of a so-called Galilean string, which now not only has transverse string Galilei boost, but also longitudinal Galilei boost. And how much time do I still have? 12 minutes. Okay, very good. And I'm on in the remaining sort of 10 minutes, including conclusions. It is in this class that we'll see, that there's a subclass of space-times in this more general Galilean Walsh sheet string theory that we find can identify the actions in near BPS decoupling limits of AdS CFT. Maybe, okay, this gets a little technical, so I'll just zoom into because you might wonder, okay, this is a very nice and compact way of writing, but these are all pullbacks of embedding fields, so it's kind of nice to write it out. And if you do that, you get, let's just skip to the, well, if you do that, it's very useful, first of all, to split your embedding coordinates into transverse coordinates xi, and a time one and one along the compact longitudinal direction that we call v. And remember, I told you in the beginning, there has to be a winding around this compact longitudinal direction. So these, the wall-sheets of these strings are cylinders. And if you then, if you don't want to look at this, it's really fine, but yeah, you can get more explicit forms like this. But I'll pretty soon make a more simplifying ansatz to get it to a simpler class of sigma models, of which I can then tell you that the near BPS AdS CFT limits are a part of. So here comes this simpler class. So theories of this form, and you see here this M field that I told about before, these transverse directions, these embedding coordinates. That's the claim here, and I will illustrate it with one little example. They can be obtained precisely by starting with relativistic strings on AdS 5 × S5 and taking this SMT limit. How does this go? Well, AdS 5 × S5 admits null killing vector, and then we can take this null reduction point of view, and then after the null reduction, so what the null reduction for us does is in some sense go to a non-relativistic string a la Gomis-Oguri, and then also take the worldsheet non-relativistic limit, and that gives you then as special subcases actions, of which, for example, the Landau-Lifshitz model is a special case. So on the next transparency, I have a little bit of more detail, not with all the steps, but so for example, this is how you can get the Landau-Lifshitz model from this prescription, from the SU2 case. So consider this, say, simplest BPS bound, where you only turn on 2 R charges on the S5. Of course, you have to put some coordinates, so we identify a time coordinate that's dual to the energy, and an angular coordinate that's dual to J. And then for implementing this limit, and you can figure out that you want to go to new coordinates x0 and u, and you will precisely see that after the limit, u becomes null. And in particular, the background that you're left with, the Newton-Cartan, or the stringent Newton-Cartan background that you're left with, takes this form. So there's a time-like field bind, there's a non-zero M field, and this transfer space. If you just plug it in this sigma model, this more general sigma model that I gave you, you precisely find the Landau-Lifshitz model. And you can also wonder, what does the PP wave that you know from AdS CFT correspond on this side, on this non-relativistic side? That is essentially the free Magnon limit, in which the S2 that you hear, that you zoom into the S2 and flattens out to an R2, and then you get this simple action, of which you can also easily show that it has a non-relativistic dispersion relation. This is to say that, so I gave you the Nambu-Goto action of this Galilean string. There's, of course, also a Polyakov action of this Galilean string, and we're examining that further because one of our goals is to quantize the theory and to see if we can understand things like the critical dimension, and of course also if we can get beta functions for these non-trivial, non-Lorentzian background fields, and can actually then sort of self-consistency would then show that particular solutions of these beta functions would give rise to the backgrounds that give you the Landau-Lifshitz model and other generalizations to higher spin groups. So this is the Polyakov action. I just want to point out that, of course, now in the Polyakov action, you want to couple it to two-dimensional gravity. But it's a world-sheet Galilean string, so that two-dimensional gravity will be by itself also a non-Lorentzian gravity. So it will be described by world-sheet Vielbeine, E1 and E0. And maybe not surprisingly, but it's nice to check explicitly that this Polyakov action has wild and local Galilean boosts that precisely act on these Zweibeine. So the punchline here is that the Polyakov action has a natural Galilean geometric structure living on it. And then, okay, we're in preparation for the quantization. We have studied the algebra of first order constraints, and that turns out to be not Virasor cross Virasor expectedly, because it's not a 2D CFT, but R cross Virasor. And hopefully this will give us a guide further to quantize the theory. Just in passing, well, I don't know if it's a curiosity, but yeah, still it's interesting to consider. You can also do the opposite scaling limit, starting with the conventional non-relativistic string, where you send this world-sheet parameter C tilde to 0. So, just want to go back. So in this action, you can also send C tilde to 0. Okay, for the non-aficionados, things where you send the speed of light to 0 are called Carolian things, and it's the opposite of Galilean. So you get a certain contraction of the Lorentz algebra that's known as the Carolian symmetry algebra. So in that case, maybe it's not so surprising, precisely in 1 + 1 dimensions, Carolian and Galilean are dual to each other, because there's only one time and one space. And again, like in the Galilean case, time is absolute, whereas in the Carolian case, space is absolute. And precisely if you have one time and one space, obviously they are related to each other by interchange. So this Nambu-Goto action of a Carolian world-sheet string is related to the Galilean case just by interchanging world-sheet time and world-sheet space. There's again a Polyakov formulation of this. Maybe not surprising, but still tantalizing. In this case, the gauge-fixed action has a residual symmetry that's BMS3, contraction of Virasor cross Virasor that plays a big role in flat space holography. But so here, it's a big question mark. Doesn't have to be related to AdS CFT, but it seems to be worth thinking about if there is some kind of limit in AdS CFT, just like I showed you before, that relates to this novel class of sigma models. And here I just wanted to illustrate again the visualization of the world sheets. Yeah, I should have put what's Galilean and what's Carolian, but this is the Galilean case, this is the Carolian case. So in the Galilean case, the world sheet is a cylinder that where you can identify equal time slices that evolve in time. In the Carolian case, so here there's a closed one form in the time direction. In the Carolian case, the world sheet is generated by time-like vector fields. That's sort of the duality also in terms of these world sheets between these two cases. Yeah, I think I'm doing well on time, so let me just highlight some further developments, in particular also that other people have been working on. I mentioned in the beginning, of course, open strings and branes. There have been various works connecting to branes, DBI actions, also generalizing to p-branes, understanding what this means in M theory. Obvious question is like, what's the supersymmetric generalization to start with of the Gomis-Oguri string? In fact, there's been one nice, or at least one nice paper using DFT techniques to sort of get the first inkling of what such world sheet action should be for the one involving supersymmetry on the world sheet. Looking into non-perturbative dualities is also sort of an obvious thing, because we have a whole web of U-dualities that we know on the string theory side. So there should be some descendant of that after the limit. Also various interesting connections to integrable models. The beta functions I already mentioned, so I'll keep it here short. Again, these connections to Carolian gravity of this Carolian string seem tantalizing, but has to be examined. So let me then conclude. So one of the things I've hoped I made clear to you is that non-relativistic strings a la GO, and GO I mean Gomez-Oguri, describes a closed subsector of relativistic string theory and has a covariant string Newton-Catan formulation that I've given you some details of, and hopefully you remember some of the geometric structures that they involve. Then a very natural question is, can this actually add something to string theory from the 90s or the 2000s? I mentioned already in passing that you can see this as a covariant formulation of the DSQ of strings. Try a more you can say a more conventional formulation, but at the price that you have to accept to be in a non-Lorentzian target space-time. One of the things we're definitely very interested in is, like I said before, to intertwine this with U-dualities and find further connection with matrix string theory and M theory. You can also wonder, are there other expansions? So that's on the, say, more like pure string theory side, independent of AdS CFT. Yeah, the other thing that I hope I made clear to you is that there's something like these spin matrix limits of n equals 4 super Young-Mills that are simpler, and in that sense, perhaps more tractable subsectors of n equals 4, for which there seems to be strong suggestion that they have a bulk description via these sigma models that I showed you in terms of some non-relativistic strings, but more like at low energies in terms of some non-relativistic gravity theory. But for that, we obviously need to quantize it. And then, yeah, similar Carolian world sheet models I just briefly mentioned. Then I think I'm precisely in time. Thanks.
Questions?
Thank you, Niels. So a couple of questions. The first one is, should I think about this as a contraction of the algebra into a smaller one? Is that the way of thinking it?
Thanks for the question. So I try to be low on the algebras, but there's a whole detailed expose of what this means at the level of algebra. I can say maybe what I found interesting, if you really like to understand the underlying algebraic structure, is that already relativistic string theory. I mean, sort of obvious also. We know this all, but it's also obvious from double field theory. It has a bigger underlying symmetry than Poincaré. Yeah. So there's what I call, or what you can call, a string Poincaré symmetry that includes the symmetries of the NS field. And you can I mean, there's a very concrete Inoue-Wigner contraction that you can do of that big algebra that includes the B field, say, that gives you the underlying algebraic structure of non-relativistic strings. In fact, then we even put all the dots on the I. You can gauge that algebra and find the geometry of the non-relativistic string.
I see. One more. So did I understand that you do not have those beta functions Or you do have
Okay,
them?
very good. So, for the, and I know there's a lot of NR here in the language, what I've repeated. So, for the non-relativistic string theories that are still two-dimensional CFTs, their beta functions have been calculated in different ways, in fact.
And so the Einstein-like equations that they imply how they look like?
Yeah, so they're known, and they're, so they involve curvatures that you can make of this string Newton-Cartan geometry. I just want to say, so, but of this Galilean string, where we did a further limit on the world sheet, which are not 2D CFTs anymore, there the beta functions are not known. And that's high on our list to do, because there we have a concrete link to AdS CFT, in fact.
I mean, I was wondering whether these non-relativistic limits can be relevant to the weak coupling limit of AdS CFT, even not for large charges, but for, in general, weak coupling limit of gauge theories in general.
Yeah, nice question. Precisely since we take a weak coupling limit. So I think yes, because let's say this Landau-Lifshitz model. Okay, for that you need then to take the large J limit. But in some sense, if you now consider quantum corrections, or well, 1 over J corrections on top of that, the fact that the starting point is a well-defined non-relativistic sigma model might help to do this. So thanks for the question, and that would be sort of the ultimate dream, that we can access this.
Any other questions? If not, let's thank Niels again.
Thanks again.